This is the ECAA from November 2020. This paper doesn't exist anymore. You'll be asked to sit the TMUA if you're applying for economics nowadays, but the bit that I'm doing, part B of section 1, advanced mathematics, just this bit here, is very much like TMUA. So this is some good extra practice to do if you want to. These questions are a little bit easier, so I'm skipping them. And yeah, section 2 is an essay question about economics, which I'm obviously not going to do. Anyway, getting into it. So this one here. So we've got some integral that has the answer of 3. So what that means is, regardless of what the function looks like, it doesn't really matter. Between 4 and 9, the area underneath the curve is 3 in total. So let's just imagine that this area here totaling 3. Now we're going to stretch the graph out by a factor of 2. And we're also going to shift it up 1. Now it's the shifting up 1 that I want to focus on. So if this graph gets shifted up one place, how much extra area is being added in? Well, we're going to add in like an entire rectangle on the bottom there. And it's going to have a rectangle of height 1 and width 5, right? So there's going to be an extra 5 area added onto this by shifting the entire thing up 1. And then by stretching the thing out by a factor of 2, you're just going to double the area that you had before. It doesn't really matter what order you do that in. No, I guess it does. You have to double it first and then shift up. But in any case, what we're going to do is we're going to take the answer that was originally there, we're going to double it when we stretch out the graph, and then we're going to add this box area 5 to it. So it's going to double and add 5, and we'll get the answer of 11, I think. Question 22. So if this and this are factors, then what that means is, if we call this f of x maybe, that means f of 1 is 0, and it means f of 2 is 0. So we substitute those things in. Of course, that will simplify to that, and when we put the other one in, it will simplify to this. This is a simultaneous equation. Let's times this one up by 4, I would guess. Yeah, and then do this one here, take away this one here, I guess. Yep, divide by minus 4 is minus 6. And then, of course, I think what we had before was a plus b is 7, yeah. So if we find that a is minus 6, then we have to add 13 to that to make 7, I believe, and we have our answer of b. Good. 23 then, so we've got an octagon here. When you're looking at areas of regular polygons, it's always good to look at the triangles that you make from kind of the center of the polygon out to each vertex. Now, I'm obviously going to make 8 of these triangles. And now, if I just call kind of this length x, and that means I can call this length x. Now, if there are 8 of these triangles, 360 divided by 8 is 45. So this angle is 45. So to work out the area of this triangle, because this length is the same as this one, it would be a half times x times sine 45. But apparently, if I add up 8 of those triangles, I'm going to get 32 root 2. And I condense all of that information here. So half times x times sine 45. 8 of those is going to give me 32 root 2. But this is fairly straightforward to deal with now. That makes x squared. That's root 2 over 2, which times by that makes root 2 over 4. That there divides to make 2. So this is 2 root 2, but the root 2's cancel anyway. So we end up with 2x squared, which is 32, divided by 2 and square root. Obviously the negative doesn't matter because it's the length, and therefore this is 4, which means the entire length PT is going to be 8. 24. So what's the area enclosed by this and this? So probably going to want to draw this, right? So there's a parabola there of half x squared. Line y equals x looks like this. And I know that it's kind of steeper than this to start with. If you want to, you can just think about what happens at minus 1. This at minus 1 is at half, because minus 1 squared is positive 1 times a half. This at minus 1 is at plus 1. So the line is above the curve here, so that's cool. But we're actually not looking at this area. It seems very obvious to look at this area as soon as you see area enclosed or region enclosed, but we're actually looking between 1, which is sort of here, and x is 3, which is sort of over here. So we're looking for all of this area here. So what I'm going to do is I'm going to integrate the curve between 1 and 3, which shouldn't be too tricky. Substitute the numbers incorrectly. That gives me that answer. So that's all of this area above the y-axis. And then what about the area below the y-axis, which I can just add to it to get the answer? Well, I could integrate the line, but it's just a trapezium, right? This distance is 2 from 1 to 3. This distance, well, this is the line x equals 1, and this is the line y equals minus x. So this is going to be minus 1 here, because it's going to be 1 minus 1 this point. So that distance there is 1. This distance here, likewise, this is 3, so this is 3 minus 3, so this distance is 3. And I can just say the trapezium is a half of the sum of the two parallel sides, so a half of 1 plus 3, all times by 2. The half and the 2 cancel, so that's area 4. And then I just need to do 4 plus this. That simplifies, I guess, to 13 over 3. 4 is 12 over 3. We add them up, and we're going to get 25 over 3. Good, 25. So we've got a field marked in here. All of these distances are the same because they're identical. So if I call this length x, then I'll call this length y, and the total length of wall is 1, 2, 3, 4, 5 x's plus 1, 2, 3, 4, 5, 6, 7, 8 y's. So I've got that, and I want to maximize xy, which is a function of x and y, I guess. Except I don't like functions of two things. So what I'm going to do is I'm going to rearrange this one for y, then divide by 8, and put it back into this function. So now this is just a function of x. And of course I can maximize that. I can expand this out. 260 divided by 8 is 65 over 2. You can halve it and halve it again, but then you can't halve it again unless you want to write decimals, which I don't. Expand out the x, of course. And now, okay, I want to maximize this. So let's think about the derivative. Fairly straightforward to work out, of course. Set it to be 0. Times everything by 8, move the 10x over. Timesing this by 8 seems annoying, but then you realize it's just what you had before, so that's nice. Divide by 10, you get x is 26. And that's actually it, because what length of WZ? Well, I labeled it, that's x, and I've got now x is 26. So that's the answer. Good. Cool. A line with non-zero gradient, that is reflected in that. This is the quickest question on the paper. The line y equals x is there. Let's just draw a line with non-zero gradient. There we are. Now let's reflect that line in this line. There we are. Now, the original line had a positive gradient, and so does the reflection. So these negatives are gone. The reflection does not have the same gradient as the thing we drew before, so it's not that, and therefore the answer is that. You can prove that if you desperately want to, but yeah. 27. 2 red balls, 2 blue balls. So let's make a probability tree, and that seems like a good idea. Red-blue is a half and half to start with, of course, because it's 2 and 2, so half chance. On the next take, though, there are only 1 red ball and 2 blue balls left, so that's a 1 in 3 of taking another red, and a 2 in 3 of taking a blue. And then likewise, this ends up being basically the same here. Now, given that one of them is red, so we're interested in everything except the blue line. So if we just do 1 minus a half times a third, that's a sixth, we get 5/6. So the probability of at least 1 red is 5/6. Just 1 take away the blue line. Now, of that, of the 5/6, so we can almost imagine this as our new total amount, because this is all we're interested in. Of that, how many have a blue? Well, either this branch, a half times 2/3, or this branch, a half times 2/3. So that's 2 lots of a half times 2/3, which is actually just 2/3, of course, so this cancels. And so our answer is this over that, 2/3 over 5/6. The 3 comes down here to make a 15. The 6 jumps all the way up to there to make a 12, so it's 12 over 15, which I think simplifies to 4/5. Ooh, does it? That seems a bit weird. Oh yeah, divide both by 3. Yeah, for sure, that's correct. Good. 28. So the sum of the first 20 terms is this. So, okay, first we're going to need this formula, aren't we? Sum of the first 20, so n is just 20. So 20 over 2 is 10. 20 minus 1 is 19. And that's apparently equal to 50. So, okay, we've got this thing here. Let's divide both sides by 10, and we get this equation in A and D. Good. So this next bit, the sum of the next 20. Now, just be careful here. Sum of the next 20. So that's not the sum of the first 40. That's the sum of the first 40. Take away the previous 20, right? That's what's going to be minus 50, because that means we're only going to have the sum of like from 21 to 40 if we do this. But of course we know S of 20, that's 50. And S of 40, we can just use this again. 40 over 2 is 20, and that's going to be a 39. And we get this, these cancel, so we get this, divide by 20, we get this. And we have a nice simultaneous equation. Although it's not that nice, because it ends up being a bit disgusting. If we do this one, take away this one, we get 20d equals minus 5. So d is minus a quarter. We can put that back into here. Times everything by 4 is the best strat here, I think. Add 19, divide by 8, and we get this. So we've got A and D now. What's the sum of the first 100? Well, again, just find out S of 100. So 100 over 2 is 50. Then you have 99 Ds here. And then you have to put in this A value and this D value, which again is not that easy. Times that by 2 to get 39 over 4. And then it's just 99 times that with the minus there. This makes minus 60 over 4, I think. What did I do here? Oh, I just divided. I took the 4 out. Sorry, I took the 4 out. 50 over 4 is the same as 25 over 2. 39 minus 99 is minus 60. And then, of course, these things you can just do the 60 divided by 2 instead to make minus 30, and then times them together to make minus 750. Good. 29. Quite an interesting question, this one. So the 50th term is 6. So x of 50, firstly, x of 50 equals minus 12 over x of 49. That's just what this looks like if you use n is 49. But I know x of 50 is 6. So I'll substitute in 6, and I can work out by rearranging this that x of 49 is minus 2. And something interesting happens here, which is if you do exactly the same thing, so set up x is 49 is minus 12 over x is 48, just following the rule again, and then put in minus 2 into here, rearrange, you get x of 48 is 6. And so of course if you do that again to find x of 47, you're just going to get minus 2 again, because it will just be the same working as this. And then you'll get to 6 again, then minus 2, then 6. And so any odd term, any x of the odd is going to be minus 2, and any x even is going to be 6, just because they're going to rotate. So okay, the sum of the first 15 terms, the first term is minus 2, because x1 will be minus 2, x2 will be 6, x3 will be minus 2, x4 will be 6, and so on. And the last term will be a minus 2, because it will be x of 15, which will be minus 2. Now how do we add these up most efficiently? Well, we can just pair them up, right? If we pair up the first two and add them, we get 4. Pair up the next two and add them, we get 4. We're going to end up with 7 pairs of 4, because that will take us to the 14th term. And then just a random minus 2 at the end. So 7 times 4 is 28, with the minus 2 at the end gives us 26, it's our sum. Good, almost halfway I think. Got a line here, mx plus c, that goes through 2, 4. So I'm just going to sketch everything that they tell me about. C is greater or equal to 0, m is greater than 0, so this looks a bit like this. This is the point 2, 4. We've got a perpendicular line going through that same point, so that's going to make a right angle. This area is 5. And yeah, this is 2, 4. So what can we do here? Well, what I can say, I think, is that if this line here goes through 2, 4, then I can just substitute 2, 4 into that line. So just putting the 2 in for the x and the 4 in for the y, and I can find c in terms of m, just by rearranging. So the equation of this this line here is going to be y equals mx, and then I've just replaced the c with more m's. And likewise, I can do the same kind of thing for this line. So it's perpendicular, right? So the gradient is going to go from m to minus 1 over m. But this also goes through 2, 4. So I'll put in 2, 4 again and rearrange, and I'll get this for k. And so I can say this line is this here. And how is any of this helpful to me? Well, what I decided to do was I decided to split this area here, or this whole area here, into like a trapezium here and a triangle here kind of thing. Because what I can say is, this distance is clearly 2. This distance is clearly 4, just because of how coordinates work. And this distance, well, it's up to the y-intercept of this line, so that's 4 minus 2m. And I can work out the area of this trapezium in terms of m. It's going to be the sum of the two parallel sides, times by a half, times by 2. Of course, this just makes 8 minus 2m, the half and the 2 cancel, so we just get this, and that's this area. And now there might be an easier way to do this. I don't know. I didn't really think too hard about most of these questions. What about this area of this entire trapezium here? Well, again, all I need is this distance, but I have that, right? I worked that out there, so that's this. And so the area of this trapezium is, again, the sum of the two parallel sides, times by a half, times by 2. Again, it works out very similar, and you get this. And therefore, this whole trapezium, take away this smaller one, given by this and this, equal 5. And this is something that I can solve for m. And even better, once I times everything by m, I get a quadratic. And that makes sense, because it's telling me there are 2 values of m possible. So this factorizes, I think, we get the value 2 or a half. The larger one is m is 2. And so that will be my answer. Okay, 31. So a list of n numbers has mean m and a unique mode d. So if we call the numbers like a1 to an, if we add them all up and divide by the number there are, which is n of them, we get the mean m, is what this is saying. 2 numbers are removed from the list. The remaining list of numbers also has a unique mode, but it's different to what it was before. Now, you need to infer quite a lot from that sentence. You need to infer that because the mode has changed, that means you must have removed 2 copies of the unique mode that it used to be, and that there was something sort of vying for this mode. It was only 1 less than it. So, for example, you had 6 7s, and only 5 4s kind of thing. And then you took away 2 of the 7s to make 5 the new mode. The new mode. So we must have taken away 2 copies of D, the unique mode before, in order to change what the mode was. So, and when we did that, when we took away these 2 numbers, the mean is now m plus 2. So I can represent this by saying this. So if I add up all the numbers, I don't know which numbers were removed, but I know that they summed to 2D. So all I have to do is just say, well, I'll add them all up, but then I'll take away 2D to represent the fact that I should be missing 2 numbers from this sum. I just don't know which, though. And of course, when I divide by the number of numbers that there should be, which is n minus 2, I get m plus 2. But of course, I can rearrange this for just mn. And I can substitute that in for all of these. And I can also times everything by n minus 2. And now, of course, when I expand this out, something nice happens, which is that this cancels with this. You divide by minus 2, and you get exactly what was required there. So quite a unique bit of thinking needed to happen to I think get to this, but quite a nice question. So 2 different geometric progressions. So okay, one of them, let's say, could be a, ar squared, and so on, and the other one s, st, st squared, and so on. The third term of both of them is 4. So both of these equal 4. And the fifth term, which is these 2, both of those equal 2. Now, if I just divide this one here by this one here, so this divided by this is just obviously r squared, which is equal to this over this, which is a half. And this divided by this is obviously squared, which is also a half. Square root, and we end up with either r is 1 over root 2 or minus 1 over root 2, and likewise t either 1 over root 2 or minus 1 over root 2. When we substitute those back into, it doesn't really matter which one, but this one here, let's say, both r and t squared are obviously just a half, as we've said here. So a times a half must equal 4, that makes a 8. But also s times a half must equal 4, that also makes s 8. So there's no choice here, a and s are both 8. But the 2 progressions are different, right? So that means while they must start at the same place, 8, one of them must have the positive ratio and one of them must have the negative. That way there'll be different progressions. So okay, we can just choose r to be the positive and t to be the negative. Why not? What is the modulus of the difference between the sums to infinity? Now, the formula for the sum to infinity is a over 1 minus r. We'll deal with the modulus in a second. Let's just first work out this sum to infinity for each of these. So okay, the first one will say a is 8 over 1 minus 1 over root 2. And we need to take away, because we're working out the difference, the sum to infinity of q, which again is 8 over, but this time 1 minus 1 over root 2, which is 1 plus 1 over root 2. Now, I don't really want to do this yet. It also says the modulus. I don't care about the modulus. I'm just going to find the answer to this. If it's negative, I'll turn it positive to get my answer. That's fine. So I'll just ignore this. But first, let's deal with this. So, okay, well, this doesn't look very nice, but I'll just tidy each up first. So let's just look at this one. 1 over root 2 is the same as root 2 over 2 by rationalizing if you want to. This is, of course, is 2 over 2, so we can now put these together to make 2 minus root 2 all over 2. But now this 2 can jump up to here to make 16. And now I can rationalize this. Times it by 2 plus root 2, both top and bottom, to make 32 plus 16 root 2 over 4. And then the 2 cross terms cancel, of course, and then minus 2, which is equal to 2. This divides, and you get that. There was probably easier ways to do that, but I got this eventually. Notice how, if you were to do the same thing with this, all that's different is there's a plus here. So plus, 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 these would be minuses, which would make this a minus. This would be the same thing because you'd have the same 2 things on the bottom. And so all that happens is you change this to a minus here. So when we do this, it's going to be this thing minus, and then the same thing just with a minus there. And of course 16 minus 16 is nothing. This minus this is 16 root 2, which is already a positive number. So the modulus thing was pointless. Now the reason it's not pointless is because remember we made that choice to make r positive and t negative. If we had chosen the other way around and done this, we would have got minus 16 root 2. And so they're telling us to take the modulus such that everyone gets the same answer in the end, despite what choice they made halfway through. Okay, 33. 2 circles have centers P and Q. Radius of each is 1. Distance from P to Q is 1 as well, which basically means they look like this, where we've got circle radius 1. The distance from the center to the other center is also 1, so they sort of go through each other's centers. But this is also 1 because it's the radius of the right circle, which means if this is 1, 1, 1, we have lots of equilateral triangles in here. Well, we have 2 of them, I guess. It's asking us for the overlap here. And the way that I'm going to work this out is, this is an equilateral triangle, like I've said. If I split this in half, I can work out this segment by doing this sector, which has radius 1, 1 and angle 120, and then take away this triangle, which is radius 1, 1 and angle 120. So that's what all of this math says. I can work out this segment by doing this sector, which is pi times 1 squared times 120 over 360. That's all of that sector. And then I'll take away a half times 1 times 1 times sine of 120, which is this triangle. And then, of course, I'm going to double it because I'm going to do this segment plus this segment for my answer. Okay, and this is obviously just pi over 3, all of that. This is obviously just a half times, and then this sine 120 is the same as sine 60 because of symmetry. So that's root 3 over 2, which makes root 3 over 4. Put the 2 through it, I guess, and we get this. Is that an answer? I hope so. Yeah, this one there. Good. D. 34. This curve has 2 distinct turning points. We see turning points, we differentiate, right? So we differentiate, that makes that. Good. What are the possible values of P for this to have 2 distinct turning points? So I want this here to have 2 solutions to it. So okay, what do? Well, I set it to 0. Of course, turning points happen when dy by dx is 0. So I want this to have 2 solutions, I guess, now, is what I should have said. So I need b squared minus 4ac to be bigger than 0. B is 6 root 5p. A is 3, C is 3p. 6 squared is 36, root 5 squared is 5, 36 times 5 is 180, p squared, minus 4 times 3 is 12, times 3 is 36. You can divide everything here by, I think you can just divide by 36, can't you? Yeah, because this had a 36 in it. So that just makes 5 actually in front there, which is nice. Factorize out the p, and we've got either, well, we've got roots at p is 0 and p is a fifth, right? And we need to be greater than 0. So you can draw the quadratic if you want to, but hopefully you're just comfortable with the idea that if you need to be greater than 0 in a quadratic inequality, you need to be either side of the roots. So either less than 0 or greater than a fifth, which is the same as 0.2. So the answer must be that one. This question was immediately followed, I believe, by another quadratic inequality, which is weird, but okay. Rearrange it, obviously. This can just factorize straight away into this. Which again, actually, and then both of these can factorize, which is interesting because they're both different z squares. Now, this is a quartic, right? I guess I was overstating when I said this is another quadratic inequality. It's not. It's a quartic inequality, which is more fun. You can sketch it, of course. It's got roots at 3, minus 3, 2, minus 2, which I know roughly over there somewhere. It's got a y-intercept of 36. It's a positive quartic, so it starts up here, ends up here. So we sketch all of that, we end up with this. When is this less than 0, this quartic here? Well, when you're between minus 2 and minus 3, or between 2 and 3, which I think is this one here. Good, getting through it. As soon as you see trig stuff, you want to only use one trig function. Let's get rid of the sine squared and make it into a 1 minus cos squared, using the sine squared plus cos squared equals 1 idea. I've also moved this over to the other side. This ends up being really nice because 10 times 1 times cos x is just 10 cos x. Minus 13 cos x is just minus 3 of them. And then 10 times this is 10 cos cubed, which we're taking away. So we just end up with 4 cos cubed. And then, of course, we can factorize out the cos x there. And we have that either we need cos x to be 0 or we need this to be 0. Those are our 2 options. This is a how many solutions we have question. How often is this 0 in this range? Well, it's there at pi over 2 and 3 pi over 2. But also, because cos is symmetrical going into the negatives, you can also use minus pi over 2 and minus 3 pi over 2. I'll get the graph in a second for if you need it. When you rearrange this, you get cos of x is 3/4, or sorry, you get cos squared is 3/4, root that, and you get plus or minus root 3 over 2. Now, when does this happen? Well, you should know the principal solution of cos x equals root 3 over 2. That's when, that's at cos is pi over 6, right? By the way, we need it to be both. We've got options of plus root 3 over 2 or minus root 3 over 2. But the first solution is pi over 6. If you're working in degrees, cos of 30 is root 3 over 2, but that's pi over 6. Now the next one, if it was pi over 6 along, the next solution over here is going to be pi over 6 back. So you end at 2 pi, cos n's at 2 pi. Pi over 6 back from that gets you to 11 pi over 6. But likewise, because you're also looking in the range up to minus 2 pi, you can have the symmetrical solutions on the other side. So you can have minus pi over 6 and minus 11 pi over 6 as well. And it's at this point that I remember that I wasn't actually being asked for the solutions, I was being asked for how many. So when you look at this line here, well, okay, you've got 2 solutions there, and you'll also have the same 2 solutions with negatives on the other side. So there's also going to be 4 solutions there. So you've got 4 solutions here, 4 solutions here, 4 here as well, and that's 12 in total, I believe. Good. It's given this and this, so expression for x. So let's rearrange this. This means y equals 2 minus x. Let's put it into there. And you can use some fancy logs straight away if you want to, but I thought it would be nicer to just say, well, this here is 3 squared divided by 3 to the x, because you take away the powers when you divide, right? But now we can just times both sides by 3 to the x. And when you've got the same indice, most people know when you have the same base, you can add the powers, but maybe a lesser known rule is when you have the same powers, you can just multiply the bases. So this makes 6 to the power x. And now, of course, we can just take log to base 6 to both sides. Now, this isn't an answer on the thing. All the answers have log to base 10. So at this point, we break out our little known change of base law, which is if you have log to base something of something, you can always write that as log to base whatever you want of the b, which was the thing here, divided by log to that same base, but whatever you wanted again, to this number here. So Taylor Swift here is just representing any number that we want. So of course I can write this as log to base 10 if I just make Taylor 10. I mean, she is a 10, obviously. And then we can make b 9, and then a is going to be 6 in this case, and we get log to base 10 of 9 over log to base 10 of 6. And that is one of the answers, which is good. Question number 38. So this immediately looks like a quadratic as soon as you look at it, if you've got a trained eye. There's a nice first step which I think is necessary, which is to realize you can move this 2 here out to the front using the power law with logs. And now, of course, if we just let y equal log to base 10 of x, this here can become 2y all squared plus y minus 3 equals 0. This becomes 4y squared, of course. Looking for the solutions of this, it factorizes, which is nice. So the solution is either y equals minus 1 or y equals 3/4. But going back to here, and then we replace the y's with log to base 10 of x, and then just raise both sides to the power 10. And this looks awkward, but actually you're looking for the product of the roots. So we're just looking to multiply these two things together, add the powers up to make minus 1/4, and that is one of the answers, which is good. Yeah. I really struggled on this question. I don't know why, because I know I've seen a question just like it before. I just couldn't remember how to do it. You sketch this graph x squared, you've got this point 0, 9 over 2, and we're looking for the closest we can get, the shortest distance to our graph. Now, this looks wonky, but that's just because I'm terrible at sketching. The distance should be the same, of course, whether you go this way or this way, and the shortest distance, of course, is going to make a right angle with the tangent of the curve itself. Again, you can go either this way or this way, which is probably why it's asking you for the y-coordinate, because that's, of course, going to be the same because it's symmetrical, whereas the x-coordinates are going to be just mirrors of each other. So that's probably why it's asking for the y. So okay, how did I do this? Well, I differentiated this to make 2x, and I called this point p squared, because obviously it's on the curve y equals x squared. So if x is p, then y is obviously going to be p squared. So okay, then I said the gradient is 2x of this curve at this point. So let's put that point in there, and we get 2p x plus c. So the gradient, well, I'm saying the gradient of this line here is going to be that is tangent at this point is the m is 2p, because the gradient of the curve is 2x. You substitute in p to get 2p, and then that's the gradient there. Now, that's useful because it means, because this is at 90 degrees, it means the gradient of this is minus 1 over 2p. And of course, I already know the y-intersect, that's 9 over 2. So that's quite helpful. And so at this point, I got really stuck, and I went down lots of dark algebraic alleys that didn't really get anywhere, until I finally realized all I really had to do was draw a little gradient triangle in here. Obviously, this distance is p, and this distance here is 9 over 2 minus p squared, which will be this bit here. And what I can say is, I know the gradient of this line is minus 1 over 2p. And I can also express it as 9 over 2 minus p squared over p, because that's rise over run. Right? Both negatives because they're both going this way, but we can cancel the negatives, we can cancel the p's, which will be very helpful. We can times everything by 2, I imagine, is what I did. No, okay, I added p squared to take away a half to make 8 over 2, which is 4, and of course p equals 2. But we were looking for the y-coordinate, which is p squared, and so therefore we have the answer immediately. Yeah, there were probably lots of better ways of doing that. I just got really stuck, and I was, to be honest, I'm pretty tired. You can probably tell by my voice. Anyway, find the maximum value of this curve here. So, I mean, gradients differentiate, right? So we differentiate to make this, which is fine. Maximum value, so we're looking for when, maximum value of this is what I'm looking for. Maximum value of the gradient. This is the gradient. I need the maximum value of this. So what I did was I decided to factorize out minus 2 to make this, and that gives me a positive here. Now you could do some kind of substitution here to give you a quadratic, but if you're comfortable, you can just work with quadratics that look like this. This is a quadratic. I can just complete the square, because if I just halve this number down to a 3 over 2 and put an x to the half here, notice when I expand this out, this times itself would be x to the 1, which is there. I'd end up with 2 copies of minus 3 over 2 x to the half, which will make minus 3x to the half. And then here, when I get a plus 9 over 4, which is why we take away this squared over here to cancel it with the plus 2 there. So this is all fine. I'll now expand back in the minus 2. This here, this is 8 over 4, I guess. This is minus a quarter. Times by minus 2 is plus a half. And now this here is a positive number because it's something squared. So that's a positive number. Times by minus 2 is definitely a negative number. So the biggest I can make this is when I make this 0, and I'll just have a half at the end. So the biggest this can be is a half. It's confusing because you think the rule is different when you have these weird powers, but it's really not. The biggest this function can be is just this thing. It happens when x to the half is 3 over 2. And so I guess when x is 9 over 4, I guess it happens, is when it happens. But anyway, that's not what it's asking. It happens when x is half. That's the entire paper. Thank you so much for watching, and I'll see you next time.